Welcome back. We'll now use a little bit of what we've learned about work and energy and the conservation of energy and apply it to simple machines, and we'll learn a little bit about mechanical advantage. So I've drawn a simple lever here, and you've probably been exposed to simple levers before. They're really just kind of like a seesaw. This place where the lever pivots, this is called the fulcrum, just really the pivot point. And you can kind of view this as either a seesaw or a big plank of wood on top of a triangle, which essentially is what I've drawn. So in this example, I have the big plank of wood. At one end, I have this 10 Newton weight, and I've written 10 in there. And what we're going to figure out is, one, how much force, well, we could figure out a couple of things. How much force do I have to apply here to just keep this level, right? Because this weight's going to be pushing on that in downward, so it would naturally want this whole lever to rotate clockwise. So what I want to figure out is how much force do I have to apply to either keep the lever level or to actually rotate this lever counterclockwise. And when I rotate the lever counterclockwise, what's happening? I'm pushing down on this left-hand side, and I'm lifting this 10 Newton block. So let's do a little thought experiment and see what happens after I rotate this lever a little bit. So let's say this, what I've drawn here in mauve, that's our starting position. And then in yellow, I'm going to draw the finishing position. So the finishing position is going to look something like this. Trying my best to draw it. The finishing position is something like this. Oh, and also, one thing I want to figure out, I wanted to write, is let's say that this distance right here from where I'm applying to the where I'm applying the force to the fulcrum, let's say that distance is, whoops, I'm using the wrong tool. That distance is 2, and from the fulcrum to the weight that I'm lifting, that distance is 1. Let's just say that just for the sake of argument. Let's say it's 2 meters and 1 meter, although it could be 2 kilometers and 1 kilometer, so we'll soon see. And what I did is I pressed down with some force, and I rotated it through an angle theta. Right? So if that's theta, then this is also theta. Right? So my question to you, and we'll have to take out a little bit of our trigonometry skills, is how much did this object move up? So essentially, what was this distance? What's its distance in the vertical direction? How much did it go up? And also, for what distance did I have to apply the force downwards here? So that's this distance, in order for this weight to move up this distance over here. So let's figure out either one. So this distance is what? Well, we have theta. This is the opposite. This is a 90-degree angle, right? Because we started off at level. So this is opposite. And this is what? This is the adjacent angle, right? So what do we have there? Opposite over adjacent. So, toa. Opposite over adjacent. Opposite over adjacent. That's toa, or tangent. So in this situation, we know that the tangent of theta is equal to, let's call this the distance the distance that we move the weight, right? So that equals opposite over adjacent, the distance that we move the weight over 1, right? And then if we go on to this side, we can do the same thing. Tangent is opposite over adjacent. So this is, let's call this the distance of the force. So here the opposite is the distance of the force, and the adjacent is this 2 meters, right? Because this is the hypotenuse right here. So we also have that tangent of theta, now you're using this triangle, is equal to the opposite side, the distance of the force, over 2 meters. So this is interesting. They're both equal to tangent of theta, so we don't even have to figure out what the tangent of theta is. We know that this quantity is equal to this quantity, right? And we can write it here. We could write the distance of the force, that's the distance that we had to push down on this side of the lever downwards, over 2 is equal to the distance of the weight. The distance the weight traveled upwards is equal to the distance the weight divided by 1. Or we could say, this 1 we could ignore, right? Something divided by 1 is just 1. Or we could say that the distance of the force is equal to 2 times the distance of the weight. And this is interesting, because now we can apply what we just learned here to figure out what the force was. And how do I do that? Well, when I'm applying a force here over some distance, I'm putting energy into the system. I'm doing work. Work is just the transfer of energy into this machine. And when I do that, that machine is actually transferring that energy to this block. It's actually doing work on the block by lifting it up. So we know the law of conservation of energy, and we're assuming that this is a frictionless system and that nothing is being lost to heat or whatever else. So the work in has to be equal to the work out. And so what's the work in? Well, it's the force that I'm applying downward times the distance of the force. So this is the work in. Force times the distance of the force. I'm going to switch colors just to keep things interesting. And that has to be the same thing as the work out. Right? Well, what's the work out? Well, it's the force of the weight pulling downwards. Right? So we have to, it's essentially the lifting force of the lever. Right? It had to counteract the force of the weight pulling downwards, actually. Sorry, I missaid it a little bit. But so this lever is essentially going to be pushing up on this weight, right? The weight ends up here. So it pushes up with a force equal to the weight of the object. So that's the weight of the object, which is, I said it was a 10 Newton object, right? So it's equal to 10 newtons. That's the force, the upward force here. And it does that for a distance of what? Well, we figured out this object, this weight, moves up with the distance d sub w. Times d sub w. Right? And we know what the distance of the force is in terms of the distance of w. So we could rewrite this as force times, substitute here, 2 dw is equal to 10 dw. Divide both sides by 2 and you have, or actually divide both sides by 2 dw and you have force is equal to 10 dw over 2 dw, which is equal to dw's cancel out, and you're just left with 5. So this is interesting. And I think you'll see where this is going. And we did a little complicated this time, but hopefully you'll realize a general theme. This was a 10 Newton weight, and I only had to press down with 5 newtons in order to lift it up. But at the same time, I pressed down with 5 newtons, but I had to push down for twice as long. So my force was half as much, but my distance that I had to push was twice as much. And here, it's the opposite. The distance is twice as much. The force is twice as much, but the distance it traveled is half as much. And what essentially just happened here is I multiplied my force. And because I multiplied my force, I essentially lost some distance. But I multiplied my force because I inputted a 5 Newton force and I got a 10 Newton force out, although the 10 Newton force traveled for less distance because the work was constant. And this is called mechanical advantage. If I have an input force of 5 and I get an output force of 10, the mechanical advantage is 2. So mechanical advantage is equal to output force over input force. And that should hopefully make a little intuitive sense to you. And another thing that maybe you're starting to realize now is that proportion, the proportion of the mechanical advantage, was actually the ratio of this length to this length. And we figured that out by taking the tangent and doing these ratios. But in general, it makes sense because this force times this distance has to be equal to this force times this distance. And we know that the distance this goes up is proportional to the length of this from the fulcrum to the weight. And we know on this side, the distance that you're pushing down is proportional to the length from where you're applying the weight to the fulcrum. And now I'll introduce you to a concept of moments. Let's see, in just a moment. So in general, if I have, and this is really all you have to learn, that last thought exercise was just to kind of show it to you. If I have a fulcrum here, and if we call this distance d1, and we call this distance d2, and if I have a force, if I want to apply an upward force here, let's call this F1, and I have a downward force F2, in this machine, F2 times d2 is equal to d1 times F1. And this is really all you need to know. And this just all falls out of the work in is equal to the work out. Now this quantity isn't exactly the work in. The work in is this force, F2, is this force times this distance. But this distance is going to be proportional to this distance. And that's what you need to realize. And this quantity right here is actually called the moment. In the next video, which I'll start very soon because this video is about to end, I'm running out of time, I will use these quantities to solve a bunch of mechanical advantage problems. See you soon.